Alright, hi folks, this is our last video of Christmas break. And I want to help you guys, since I managed to confuse everybody on shapes and how things arrange themselves in space. We'll have a quick review now, try to get it straight. So remember the Vsepr theory, the valence shell electron pair repulsion theory, tells us that because electrons are all negatively charged and like charges repel each other, things will arrange themselves in space so as to keep their electrons as far apart as possible. And of course we know that if you arrange four things in space, just keeping them on one flat plane doesn't get them as far apart as they possibly could be. Imagine my hand's the fourth thing. But orienting them in a three-dimensional structure is going to help get them further apart. So we're going to try to draw that on a two-dimensional board or piece of paper to show the structure, and then we'll build some models in class with gumdrops and stuff, yay, as a reward for your hard work at all those worksheets I gave you over break. So PCl3, well, how would we name that first off? Well, that is phosphorus trichloride. You can tell you'll name it as a covalent because it's all non-metals. Phosphorus trichloride. And then we need to draw Lewis structure to figure out what shape it will need to be to get its electrons as far apart as possible. So P, you can see, is in the fifth column here. So it'll have 5 electrons in its valence. Use your periodic table on the test, on the quiz, everything, just to make sure that you know. So 1, 2, 3, 4, 5. Phosphorus is 5 over, so it'll have 5 valence. So P, 1, 2, 3, 4, 5. And then Cl, chlorine, of course, has 7 in its valence, and there are 3 of them. So maybe I should move my phosphorus over and figure out how to arrange those chlorines around it so they fill in all the gaps. And this one's pretty easy. So I'll put my phosphorus in the middle because it has the most holes. It has 5 valence electrons and chlorine has 7. So I'm going to put the pair on top and the other 3 around it like that. Chlorine has 7, so it kind of has one free space. It can fill in these gaps like this, this, and this. And of course each chlorine will have its other electrons around, which you do need to draw. Color really helps, I find, when I'm studying these things, trying to build structures. So I can see whose electron used to be whose, although of course covalents will share them equally or unequally if their electronegativities are different. But electrons are impartial, they don't care which atom they're around at the moment. They move pretty freely. So you can see here that if I drew a nice neat line structure for that, I would have this unshared pair on the phosphorus, and then just these single bonds with the 3 chlorines. And then of course the chlorines always have those dots. Okay, so when you have something with 3 things arranged around it and the 4th thing is an unshared pair, you know that the unshared pair exerts a greater repulsion to the other electrons and takes up a little more space. So as it bends these, of course it would be better if I drew maybe a dashed line here and a little wedge here to show that this will arrange itself so that that chlorine would go back into the board, this chlorine would pop out, and this chlorine and the unshared pair could be on the same plane as the board. So we'd have a 3-dimensional structure, but that pair is going to bend the molecule just a little more than a normal tetrahedral shape. So its bond angle is actually going to be 107 degrees. And that is a pyramidal shape because the 3 chlorines would be pushed down to form like a little pyramid underneath, because the unshared pair will take up a lot more space in its area. So we'll call that pyramidal. So phosphorus trichloride, pyramidal shape, each bond angle will be 107 degrees. Oh, and this is important. Please find your protractor, wash it, because it will be touching food that you might want to eat at the end, your gumdrops and marshmallows and such. Wash your protractor before class, wash your hands before class, and then we can try to measure some different bond angles and try to get our structures as close as possible. So, structure for hydrogen, the homonuclear diatomic hydrogen in its elemental form. So you know hydrogen is kind of that exception. Instead of 8 electrons in its valence, since its outer shell is the 1s shell, it will only hold 2 electrons. So hydrogen's going to want 2. Each hydrogen, of course, has 1. So it will come together like this and form a single bond, which we can draw thusly. And 2 things single bonded together are just going to be in a straight line. So that'll be linear, and of course you know a line is 180 degrees, so that's an easy one. Then this silicon and chlorine come together to form both nonmetals, so they'll form a covalent compound, silicon tetrachloride. We can look at the periodic table and see that silicon will have 4 electrons in its valence. Of course, we know chlorine has 7. So we'll put silicon in the middle, and it'll have 4 electrons in its valence because it's in row 4, just like carbon, for example. Chlorine then will come in and fill in these places. Okay, so silicon trichloride, and it will have a tetrahedral shape. So I'll write that out here, tetrahedral. And the bond angle on tetrahedral is 109. My memorizing skills, oh good it is, 109 degrees. When you draw the line structure for that, you want to draw 2 of the chlorines in the same plane as the board or the paper, and of course they'll have their unshared electrons. And then the other 2, one with a dashed line so it is represented going back into the board, and one with a wedge like this, so it's coming out. And you'll see the shape so much better when we're able to build the molecules with real stuff in 3 dimensions. Then here we've got H2S. Oh, I didn't tell you, these are the practice problems from the textbook. So this practice problems for Module 9, problems 4, 5, 6, 7, 8. We probably won't have time for them in class, so here they are. So hydrogen and sulfur, this would be hydrogen sulfide. Hydrogen, of course, has 1 in its valence and wants 2. And sulfur, if you look at the periodic table, it has 6. So we'll put it in the middle, it has the most holes. So S with 1, 2, 3, 4, 5, 6. Then the hydrogens will come in with their 1 here and 1 here. So when you have 2 unshared pairs, how can that be arranged so that everything is as far apart as possible, considering that the unshared pairs take up a little more space? This is exactly the way that a water molecule is. So this is a bent shape, bent, and that's 105 degree bond angle, 105 degrees. Yes, good. Okay, so bent shape, 105 degrees. So it's going to look just like a water molecule. And so when I draw its line structure, I'll just draw it in the right shape. So those hydrogens come down here. Of course, you can see that sulfur and oxygen are in the same column of the periodic table. So just picture that as an O, and you'd have H2O. So very, very similar chemistry, except that this doesn't do hydrogen bonding like water does, so that this is a gas at room temperature, and you know, we're thankful that water's not, because that makes us alive. So here, when you have two unshared pairs like this, of course it arranges itself similarly in that tetrahedral kind of way where the unshared pairs would be oriented like this toward the board, and the hydrogens in the plane of the board. That's sort of hard to draw, and it'll be easier for you to see when we really build it out. But that's a bent shape. Since these take up more space, instead of the 109-degree angle, they hog some space and cause these angles to be 105 degrees. And the last one, which kind of looks similar, CS2, so that's carbon disulfide. So we would have a carbon in the middle because it has more holes, 4 electrons in its valence. And then sulfur, we just talked about, has 6. So we'll plug those in. So sulfur, 1, 2, 3, 4, 5, 6. And then I'll draw the other one in green just so we can really see where those electrons are. 1. And then I'll put the lonely one up here, 2, 3, 4, 5, 6. Then you can see that we're going to have some double bonding, and we'll form a double bond between these. Here's a single bond, and then a double bond between these. So each sulfur will be double bonded to the carbon, a single bond here, and then the double bond here and here. So what we'll end up with is S double bonded to C, double bonded to S. So always check, especially when you're dealing with double, triple bonds, make sure that you don't put more than 8 electrons around any given atom. Check every atom. So you can see that each sulfur has 2 unshared pairs. 1, 2, 1, 2, 1, 2, 1, 2, and then count. This has 2, 4, and each line, of course, is 2, 6, 8. 8 electrons around the sulfur, 2, 4, 6, 8 around the carbon, 2, 4, 6, 8 around that sulfur. Everyone has their octet, but you do have to be careful because sometimes you can throw in triple bond here and a double bond here and not realize that that center atom has 5 bonds around it, which of course violates the octet rule, and you can't do that. So make sure you count. So when you have these double bonds like this, you're going to end up with a linear molecule because double bonds really kind of lock things into position. So this will form a linear shape at 180 degrees. And when we get to class on Tuesday, we'll you'll have the answer sheet for this, but we'll go over these in class and then build them with our fun model kits. So make sure you've really looked at that and you're prepared with the proper shapes. Memorize the shapes, memorize the bond angles, practice Lewis structures, and that will definitely be a big part of the test. So have a good week. See you soon.